Hi, so we are very happy to welcome Saporta-Katz, who will talk today about a kinematic-dynamic 3D model for density-driven ocean flows, and she's from Weizmann Institute. So Ori, take it away.
Thank you very much. So hi everyone. Today I'm going to show you a model for ocean flows that I built along with my collaborators, Idris Tidi, Chezi Gildor, and Meridional. The first approximately half of the talk will be to present the physical and oceanographic motivation for this model, why we wanted a new model, and how we built it through the physical considerations. And the second half, or however much time we will have left, will be to discuss the existence, uniqueness, and bounds that we proved for this model as an abstract PDE model. So yeah, let's start. Okay, so the first, and I'm putting my own presentation here also, so I won't forget things from my notes. So the basic physical phenomenon that is underlying our research is a density-driven circulation. Okay, great. So think of a box of water that is divided into two parts, and one part is denser than the other part. For example, it can be saltier than the other part, or it can be colder than the other part, which are two tracers that are relevant for the ocean. As soon as we lift the boundary between the two parts of the water, then of course the heavier water, which is colored here in blue, will sink underneath the lighter water. And if there is some kind of physical mechanism that retains higher density in one part than the other, then you can imagine that a stable overturning circulation will ensue from this situation. Good. Okay, so ocean density. So we're talking about the density of water in the ocean, and the relevant tracers that are in charge of density in the ocean are temperature, salinity, and pressure. And what I'm running here is the linear equation of state for the water. And you notice that I don't have P here, I don't have pressure here. And the reason for this is actually potential density, because the pressure effect at the same depth is approximately the same. So potential density is the density that a body of water would have if you would take it adiabatically to atmospheric pressure. And this is the relevant equation for our system. Oh, and wait, can you go back?
Oh, yeah, sure.
Say something? And what you can see here is the temperature and the salinity in the North Atlantic Ocean. So blue is colder than red, and here blue is less salty than red. So if I ask you where the water is denser, in the north or in the mid-latitudes, then you can see that you have a conflicting situation here, because colder means denser, but saltier means denser. So the winner, salt or temperature, will be related to exactly who our coefficients here are, alpha and beta, what their identity is. And you will see that this is important for our model. Okay.
But why don't you have another graph for the density?
Well,
you have it, or
I'm gonna answer this question next. It's like a teaser.
Okay.
Okay. Okay. So what are some real world examples for this type of density driven flow? So one situation is called estuary flow, where a freshwater river meets a salty sea. So we have fresh water meeting salt water. We have a difference in density that results in an overturning flow. Another example is in the Mediterranean Sea itself, in the Gulf of Lion, where we have intense winds between the Alps and the Pyrenean mountains that cool the surface waters intensely and result in them being colder and also saltier, because there's a lot of evaporation from this wind. And there is also an overturning circulation that happens in the Mediterranean as a result of this area. And our motivating example is the Atlantic Ocean, where now I will tell you the answer. The north is denser than the south, and therefore we have a globally encompassing thermohaline circulation, of which the Atlantic branch consists of a surface warm flow that is going to the north and then sinking in the north because the water there is, as we said, denser, and then a return flow that goes southwards along the depth of the ocean. And the reasons why the water in the north is actually denser than the water in the mid-latitudes is complicated. And one of the reasons that the water is denser in the north is because of this circulation itself that advects salt to the north. So there is a kind of feedback effect here. And as you can see, it could be, as it will see, it could be the other way around. Yeah, okay. So that's, this is the relevant side for what I'm saying now. And this brings up the question, how stable is this overturning flow? So this overturning flow, we care about its stability as scientists, well, let's say it this way, geophysical scientists and climate scientists care very much about this overturning flow, as should we all, because it is responsible for transferring warm water to the northern latitudes. And along with westerly winds, this is one of the reasons why, for example, England is warmer than its counterpart at the same latitude in like northern Canada, because this water is warm along the surface and then winds advect this warmth to Europe. And in other words, this circulation is very important for the global climate. But how stable is it? Because as you can see, we have here a game between temperature and salinity. And as it turns out, this is going to turn out to be a bistable system that could have an opposite flow. Okay, let's continue. And of course, what is the effect of global warming? Melting icebergs, which bring cold, fresh water into the ocean, changing flows. Okay, so our motivating question is, what are the dynamics of a realistic density-driven overturning circulation? And we're looking for a model that can kind of address this question. Okay, so let me show you a very simple, very elegant model that is extremely insightful, that was thought up by Stommel in 1961. So Stommel envisioned two basins of water, one with salinity S1, temperature T1, one with salinity S2, temperature T2. Each one of them is connected to a thermal and salinity bath, and there is a flow between these two basins, where the flow is through a capillary Q, and the strength of the flow is proportional to the difference in densities. So the more box 2 is denser than box 1, well, in the case of this arrow, actually, the more box 1 is denser than box 2, the flow will be quicker, and vice versa. And what we can see is that given the same forcing, we can have a bistable regime where we can have a stable overturning flow that goes in the clockwise or in the counterclockwise direction. And this simple model just shows this in a very simple ODE equation set. And this, of course, immediately instigated the thought about the real AMOC and can it switch directions. And this idea even made it to Hollywood. So the movie The Day After Tomorrow is a movie about what would happen to Earth if the overturning circulation would stop. The physics here are okay in terms of global warming, melting icebergs, cold, fresh water is poured into the northern latitudes. This could actually, this could physically cause a stopping of overturning circulation. However, the timescales here are completely mythical. It would take thousands of years probably, or hundreds of years, and not 2 days, which is what happened in the movie. Okay, so let's move to a different ocean model. And in our model, we basically combined 2 ideas. Let's talk about an ocean model for kinematics. So the realistic flows are intricate and usually chaotic phenomenon. And here is a very simple model for the North Atlantic surface flow. So in the North Atlantic, we have generally 2 gyres. It's a double gyre flow. The sum of parts of this gyre are termed the Gulf Stream. And this is basically the backbone of the surface flow in the North Atlantic. This can be approximated by 2 asymmetric gyres in a box. And in 1993, Liu and Young showed that the 2D oscillating double gyre flow exhibits chaotic advection. So let's explain what I mean. Oscillating, it means that the black line between the gyres goes up and down. This is a 2D flow. And chaotic advection means that of course, it's just a Lagrangian advection. So the transport between of 2 points that start very, very close together can be exponentially separating. And this phenomenon that is called chaotic advection results in mixing between the gyres when the oscillating demarcation line is oscillating in the correct So if you recall some fluid dynamics or fluid kinematics, a 2D preserving flow is, of course, laminar. It is not chaotic. In order to get chaos, we need chaotic advection. We need to have a 2D time-dependent flow. However, in 3D, this limitation does not exist. In 3D, we can have chaotic advection even in a stationary flow. This is just kind of a remark that may be relevant. Okay, so if we want a very, very, very simple model of the North Atlantic flow, we can take this double gyre surface flow in a 3D box, put it on the surface with some exponential decay as we go down in the depth. And in the vertical direction, we can add a overturning flow, which approximates the AMOC, the realistic overturning flow of the ocean. And we get a 3D, perhaps time dependent if this is oscillating flow. And this flow as U is built, we define here UE, which is the surface flow, and UI, which is the overturning flow. E is for external, since this is wind driven, so it's driven by external forces. I is for internal, since this is density driven. This flow is driven by density, so it is driven by, in a sense, internal variables. So UE and UI. I had a movie of what the trajectories look like. It's just pretty, but it's not going to work because this is the PDF. So I can try to show it later if we have time. Okay, so let's start building our model. We want to build a model of ocean flow in a box that has a flow which contains a component that is externally activated. So for our needs, it is predetermined. It's a predetermined function of space and time. And we add to it a dynamic component which has a constant spatial form, but its strength is a function of the density. And this is kind of how we combine the box model with the kinematic double gyre flow, or any kinematic flow that we want. We can put here any velocity that we want. And the important thing is that the dynamics are all encompassed in this AI, which is the difference in density between the northern box and the southern box. So this is the dynamics. So you can understand that what we're describing here is a box in which there is water, which contains temperature and salinity. And the flow is moving the temperature and salinity around, while the temperature and salinity change the density, which is controlling the strength of the flow. So we have here dynamical system. Okay, so what is the full kinematic dynamic model? We want to talk about the advection and the diffusion of temperature and salinity. So we just take the advection diffusion equations for temperature and salinity, advection, diffusion, and sources, where the coupling, if this would be just a linear model, it would not be interesting. The coupling between these two equations is through the velocity field U. The density is a function of T and S. We're taking only the linear approximation. It's a linear approximation of T and S. And the velocity field is some predetermined velocity plus a dynamical strength. So it's just the coefficient, which is dynamic. So this is just a number times whatever we take to be the internal flow, which, as I explained to you, we're taking this kind of overturning circulation, and we add to this boundary conditions, and we get our kinematic dynamic model. And in the second half, which is coming up, I will get more into the equations of this model. And I want to emphasize that the flow itself, the UE and the UI, could be any incompressible flow that depends on space and time that we choose. Since our motivating example is the North Atlantic, then I'm showing you how we take the double gyre with the oscillating demarcation line and the overturning flow.
Mm-hmm.
Oh. There we go. But it could be basically anything, and this model is very versatile and could fit many physical systems. And basically our dynamical question or our oceanographic question boils down in this formulation to a very simple question. What are the dynamics of AI? So AI, notice that it's AI, kind of, never mind. It's the internal strength of the internal velocity field, which is simply some coefficient times the difference in density between the two boxes. It's a number, it's a one-dimensional variable, and it basically encompasses the entire dynamics of this three-dimensional plus time partial differential equation set with integrals. Okay, I forgot to say something about the integrals. So we want the density in the two boxes, the difference in the density between the two boxes. So we're taking the average density over the boxes. So the average over B2 minus the average over B1. And each average is, of course, an integral over the density of the entire box. So it's an integral partial differential equation. And all of the dynamics are encompassed into this small variable AI, if it's oscillating, if it's steady, if it is chaotic. This is what interests us both from oceanographic reasons and for okay, so what can we do with this model? I'm just giving you here just kind of proof of concept that this thing is okay. So we can set the parameters in such a way that we are recreating the Stommel box model, and we get the same hysteresis loop. I'm not going to get into the details of these graphs right now, but we get the same qualitative and quantitative behavior as the Stommel model, where we have a bistable regime where clockwise and counterclockwise flows are stable. So this is setting the parameters in a very specific way, just to copy the Stommel box model. So this is kind of a proof of concept that everything works, that our simulation works, that our model is okay. And then we can go to the other complexity extreme and kind of fit all of our parameters to fit the North Atlantic Ocean. And we are comparing here results from our model to results from the North Atlantic Ocean itself. And well, you can see qualitatively, at least, And it's also pretty good quantitatively that there are similarities between the sea surface temperature, sea surface salinity, and also the density. There is one thing that we haven't yet solved that we have to add to this model, which is a mechanism to solve density inversions. So in our steady state that we reach in the North Atlantic Ocean, we have that the water on top is denser than the water underneath. This is physically unstable, but we don't have a mechanism in our model to fix it. So we need to add something that mixes vertically when the density is higher in the top. Something to some dynamical model that is coming instead of gravity, because we're not solving the physics, so we don't have gravity. Exactly. Okay, so soon I will show you what this looks like as a PDE model, for which we proved these two theorems, which is that given initial conditions T0 and S0 that satisfy some regularity constraints, the model has a unique global and time strong solution that depends continuously on initial conditions, boundary conditions, and sources. This is basically the definition for Hadamard well-posedness. And we also showed several bounds on the solutions, so we can say something about these solutions as well. And also, if everything is time independent, then the model has a steady state solution, doesn't change in time. And if the Rayleigh number is small enough, then all the solutions will converge to a unique steady state solution as T goes to. Okay, this I don't want to get into. I'll get into it maybe on the board, allowing time allowing. And also the generalizations I want to talk about when we reach the point. So can you go down two more? One more, that's it. No,
Okay.
up.
Okay.
Summary. We have built a new model for density-driven flows, combining the box model, that Stokes box model, with the kinematic model. The dynamics of the model are encapsulated in a single variable AI. Well-known solutions to box models are recreated with these, and we can set the parameters to recreate the North Atlantic Ocean. From the oceanographic perspective, we want to ask what happens when we have changing sources. What is the stability of the overturning simulation? We want to, now that we have our model, we want to go back to the oceanographic question. From the mathematical perspective, we can ask if the diffusion is small enough, do we get a chaotic attractor? So as you saw, we can take an external flow that has chaotic advection. How is this translated into our dynamical system since we have diffusion? Does the diffusion automatically kill all of the chaotic attributes, or can we get a chaotic attractor? Yep. So, okay. So any questions at this point?
Yeah. Why is this an open question?
We haven't answered it yet. We need to prove it, if it exists or not. We think that that we can get a chaotic attractor, but we need to show it.
What do you see this in simulation?
Yes, but it's not clear at the moment if what we see in the simulations is realistic in terms of the, okay, we can set the parameters to some extremes, and we see something that looks like a chaotic scenario. However, first of all, it could be an issue of numerical stability and not of dynamical chaos. And second of all, we want to, we want to see if we can get a chaotic attractor for physical parameters. Like, what would be the bounds on the parameters that would give us this? Is the actual ocean capable of this chaos, or is it just some extreme of parameters that is not relevant for any water system? So a rigorous proof could give us an answer to the first question and a direction or some bounds for the second question that might be useful. Yeah.
Could this also be applied to inland case, for example, of the case in China or
Which case?
I mean, just now I see your model is mainly about the oceans. I mean, could it also be used applied to inland case? Inland, for example, Chinese mainland.
Yeah. Yeah, I mean the ocean here is our motivation.
Yeah.
And also the fact that we're using temperature and salinity to determine the density. So if we're looking at freshwater,
But just now your model was mainly about the ocean, and but then maybe inland countries may also have some lakes or
Right.
Rivers, like Chinese yellow rivers, or America also many famous rivers.
Yeah, it can be applied to that. We just have to fit the parameters to an inland salinity and an inland temperature and the flows.
Do they differ with each other very much or similar or
The ocean or the
Yeah.
the ocean versus the
with
The main difference is that the salinity in the ocean is much higher than the salinity in inland streams and rivers. Still, you could have the same type of phenomena inland due to differences in temperature. So you could also get an overturning circulation. This model is relevant for everywhere that you get an overturning circulation. When can you get an overturning circulation? When you have a difference in properties of the water, in density of the water between areas that are touching each other. So for example, if you have a river that is meeting another river and one river is, I don't know, more polluted than the other one, it'll be denser than the other one. And you could have an overturning circulation in this situation as well, and this model could address it.
Okay, thanks.
Okay, so I think we're gonna, well, maybe I'll use this part of the board, at least to start. I don't know. This one needed to,
Close it?
I think so.
John, you say that there's a nice video.
Yeah, there's a nice video of the projection. Maybe it's on PowerPoint. Can you
Yeah.
open the PowerPoint? Please. Can you open the PowerPoint with
Yeah, sure.
Let's see, can you go down to more down, more. Oh.
Yeah.
Okay.
No.
Let's see if we can show it.
No, that's not. Oh, it
This
isn't.
is the PowerPoint. Yeah, can you go
Yes.
more? Yeah, more. One more, two more. Well, this one.
Yeah.
Does the video work? Yes,
Yes,
it
it does.
Okay, so can you do
Sure.
okay, so this is what Lagrangian trajectories look like in our model when the demarcation between the two gyres is oscillating. So you can see these symbols. And can you do play on the left one?
Yes.
And this is what they look like when it is not oscillating. Yeah, this is just kind of to give the understanding. And can you press play here too? It'll do them both simultaneously. Or not. Yeah. Oh. Okay. Oh, it's not working.
Yeah.
On my Mac it works. Okay. So yeah, you get the idea. What you can see when you see them one next to the other is that here you can really see the chaotic advection. So you can really see the mixing. Here you see that the colors are kind of together. So you can see these lines of red and yellow and purple. And here you can see that you can see the mixing better, but it's not working. So.
Yeah, for some.
Can you try to press just like in the middle of the movie? Just like.
Yeah, here it is.
So you can see that it's better mixed. This needs to be quantified, but yeah, even though 3D stationary flow can have chaotic advection, this chaos is kind of constrained to small regions, whereas in the 3D time-dependent flow, we get a good amount of mixing of chaotic advection in a large area. Okay, so now in the time remaining, in the 20 minutes approximately that I have remaining, I will try to bring us all to a point where we understand the theorem. As well as
You have more time if you need it.
we'll see. I'm trying to.
Would you like me to turn it off or?
Yeah, let's turn it off and turn it on.
This is something button.
Oh,
Really? When I put it down, it was just mechanical.
minutes. Oh, no, I shouldn't turn it off. Sorry.
Why not?
Because of this.
Oh, okay.
Yeah.
I'll start running. So let's start with our domain. We have a box, which is so we have a one-on-one box, which is called omega.
Yeah, I'm sorry about that.
It's okay. Yeah, good. And this is our everything happens inside of this box. A point in the box is denoted R. Omega, a point on the boundary of our domain is denoted Q.
Here.
And the normal to the boundary, outward normals is denoted N of Q. The top of our box, we call it sigma 1, and it actually just equals x, y, z equals 1. Omega. Oh, it's not in omega, it's in omega. Yeah. Let's put it here in the boundary of omega. And it is denoted the surface of our ocean. Good. That's our domain. And now we divide our model, and of course, simple generalizations are to take this domain to be any rectangular box that we want, or actually any shape that we want, because we can always kind of take a box and put any intricate topography inside the box and just set the rest of the box to be 0 with appropriate boundary conditions. So that's an immediate generalization. The ocean does not have to be an actual box. So we want to divide this into boxes. So very simply, we just put some division on our inside of our box, and we call the two parts, V1 and V2, such that V2 are omega, and their union is omega. It didn't have to be this way. We could have them smaller than omega. We could divide it into more boxes. I had a slide about generalizations, but I skipped it for now. But it's pretty modular, and our proof holds for the modular setting and not just for this setting, which is nice. Okay, and we also want to define a notation. So let's say that we have a function phi, which is L2 of omega. Then we just want to denote these brackets. Bracket phi I is going to be the average of phi over box I. So it's going to be the size of box I, 1 or 2, times the integral of phi over the same box, volume integral of phi. So it's just basically the average of our phi on one of the boxes. And we also denote phi with no subscript to be the vector phi 1 and phi 2. This is terrible. Okay. Okay, you get the idea. Next, we need, in order to have the setting of our problem, we need additional conditions. E0 and S0, which at first, let's just ask them to be L2, such that, and we're looking for solutions T and S, such that T at time 0 will equal to 0, and S at time 0 will equal S0. And finally, we want our boundary conditions. And boundary conditions, we're going back to physics. So we need boundary conditions for temperature and boundary conditions for salinity. What happens in the temperature? In the temperature, the situation in the ocean is that the ocean wants to equilibrate with the atmosphere. So if the atmosphere is warmer, the ocean will want to be warmer. And if the atmosphere is colder, the ocean will want to be colder. But if the ocean is the same temperature as the atmosphere, it will not change its temperature at that point because it is equilibrium, right? So this motivates the use of Robin boundary conditions for the temperature, or also known as restoring boundary conditions, which means that the normal derivative of the temperature will be some coefficient, Nusselt number, times the temperature in the atmosphere, which is denoted as T star at a certain point, minus the temperature at that point. So if they're equal, we have no flux of temperature. If they're different, we have a flux of temperature that is proportional to the difference in temperature. And this happens only on the surface. And if we are at the other boundaries of the box, we have no influx of temperature. So just 0. On the other hand, the salinity, physical thing that changes the salinity in the surface of the ocean is, well, there's no rain of salt. into the water. There's only evaporation and precipitation. So there's only loss of fresh water and addition of fresh water, which is why the amount of salt is basically constant. But in any case, the evaporation and the precipitation does not depend on the amount of salt in the ocean at the moment. So we don't need this type of boundary condition. We need a predetermined flux boundary condition. So it's a Newman boundary condition. So we're basically taking evaporation and precipitation, which is the removal and the insertion of fresh water, and we are translating them into an artificial insertion and removal of salt itself. And we can do this since the amount of water in the ocean is approximately constant. So it's not that there is a large amount of water being removed or added to the ocean at a given point. And also, overall, over the entire basin, we require that the change in salt is 0. So again, we have this time we have the Sherwood dimensional number times star 2, which is the insertion of salinity or the removal of salinity from the atmosphere. If Q is on the surface, or 0 else. Okay. And again, overall salinity is not expected to change. Another way to say this is overall amount of water is not expected to change. So we also require that the integral of S star, which is some function of U over sigma 1, is 0. So there is adding salinity here, there is removing salinity here. Okay, so this is our setting. And now, so good to have this part. I'm gonna write this more compactly because I need one more part of the board. The eraser?
Yeah. Mhm.
No, it works. Eraser. Is it the eraser? I don't know. Probably. It was very dusty. Okay. Okay, so we have our setting, we have our domain, we have our initial conditions, we have our boundary conditions. Let's add our equations. So we have the advection equations with sources coupled to the velocity more linear okay. This then explain what you already saw in the presentation. Okay, so change in time of temperature equals the diffusion minus the advection I'm not writing what these are function of, but later, it just takes too much space. Plus source string, ft, which could be a function of time and some predetermined function, not coupled to the temperature zone. Same idea for the salinity. And for the same idea that we don't want to add or remove salt, or we don't want to add or remove water, we are requiring that Fs can be any equation, but it needs to satisfy that its integral over the entire domain is 0. So if we're adding salt somewhere, we're removing salt somewhere else. Okay, so our coupling is through U, and who is U? U is our velocity field. And as I showed you in the presentation, U is going to be a function of space. It's going to be a function of time. And it's also going to be a function of the averages of temperature and salinity, which together give us the average of the density. So it's going to be the Piclet number times the external U, UE, and UE is external. It is predetermined because it is not dependent upon temperature and the salinity. So it can be a function of space, it can be a function of time, but it is not a function of temperature and salinity. The Piclet number basically gives us the dimensionless ratio between the advection, the strength of the advection, and the strength of diffusion. So our diffusion, our kappa will be 1 in this formulation. So Piclet is telling us how important is our external flow in relation to our diffusion. And the more important it is, the more chaos we expect. The more diffusion we have, the more our problem will be regularized. And the same for our thermal Rayleigh number times AI of rho, which is a function of T and S, and I'll write it down in a second, times U, again, can be a function of space. Who is left? Left is to say who is AI. AI is just the density in box 2 minus the density in box 1, which is basically in renormalized parameters, it is minus the temperature difference coefficients times the salinity difference. Okay, so that was a lot of work just to present our problem. And as I said, kappa itself is it's delta 1, and physically delta is of order 1. Okay, so that was a lot of work just to present our model, but this is our model up to generalizations that we can make. Okay. So what generalizations can we make for this model for which I will propose? We can take any number of boxes that we want. We can have the boxes be any shape that we want. We can take any velocity field that we want and as many components of velocity that we want. We can add here other functions of T and S, addition, subtraction. What can we do? We cannot to t squared here. Proof. It is clear why not. At least not with our proof holding exactly as it is. Okay, so that is our problem, and what we want to prove, write that down.
So yeah.
Other notes. Lazy to actually write it down. And with this, I will finish. I just want to write down it should be written. Maybe just say one word about it. Okay. So
The theorem is that there exists T and S that are strong solutions, global in time, solutions to the PDE set. That satisfy the initial conditions. In some sense, they satisfy the boundary conditions. These solutions exhibit continuous dependence on problem parameters. Okay, so what do I mean here? So first of all, when I say strong solution, I mean a solution that satisfies these equations almost everywhere. We would, of course, like to have a solution that satisfies it everywhere, but we don't need it. There are also conditions to get a classical solution. But in fact, if you think about it, the physics, if you think about it, about what these equations are actually talking about, they're talking about water, right? Now, water is built of particles. So if we look at it from a physical perspective, we would not expect better than a weak solution to these equations, because we don't want these equations to be true everywhere. Because if you go down, zoom in into the water, then you don't have a continuous entity. You have a discrete entity that is built of water particles. So getting a weak solution is definitely good enough for the physics, and it is also good enough for simulations, in which we also discretize our space. And we have better than weak solution. We have a strong solution, but for me, that's a bonus. Weak solution would be good enough for sure. Continuous dependence on the problem parameters, that's important because we have invented a partial differential equation set here. And if we take a partial differential equation set from a box that is nonlinear, we have no guarantee that it is well behaved. But we want solutions that are physical, which means that if we change our, for example, our initial conditions by just a tiny bit, we want our solution to change by just a tiny bit. We want this continuous attribute. So that is about continuity. We have also shown bounds on solutions, so we can actually say something about the solutions analytically. So we can say something about the L2 norm of T and S, the H1 norm. And this is nice because it allows us to kind of check ourselves if we're okay. And
pretty incredible that we can say something analytical about these solutions to the equations other than the numerical solution. Yeah, and also we can have some regularity conditions in which we get a classical solution. That's nice. So that's one theorem. And it's pretty, I mean, it's what we would expect. If we wouldn't have this, we wouldn't have anything. But the second theorem is kind of a bit nicer. So I'll just write it down. And I think that will be the end. So the second theorem is talking about steady state solution. So theorem C2 is that if all problem parameters functions are time independent, so S star and T star and FT and FS and UE and UI, if they are all time independent, then the system has a weak steady state solution. That satisfies some bounds, and if the maximum of, well, I didn't present salinity Rayleigh number, so let's just write it this way. If the Rayleigh thermal number is small enough, smaller than some function, I'm not going to write it down, of the domain, the Nusselt number, the Sherwood number, the delta number, all of these dimensionless parameters, source functions, then all solutions converge to a unique steady state solution. And this brings us back to the question of that bistability that we saw. So if we have a single unique steady state solution, we have no bistability. So this is basically saying, okay, so if we raise the diffusion enough, then all solutions will converge to a unique steady state. We will lose our bistability, and we see this in the simulation. We see this as well as analytically. Okay, so that's what we have proved. It all appears in our paper. The next thing to prove is to show that even if the problem parameters and functions are time dependent, if they are periodically time dependent, like for example, in the real world, we have weather patterns, so in a sense it's periodic, then we have a periodic solution. And of course, the question of the chaotic attractor is the question of what happens if the Rayleigh number is big enough. If it's big enough, can we get convergence into a chaotic attractor of our solutions in functional space? Is the attractor of our solutions chaotic? Yeah, so I think that's enough. Sure. Thank you.
Are there any questions?
Say a word about the proof itself, but I mean, yeah, so it's nice actually. Yeah.
So if the precipitation is in solid state like a snow, does it affect your model or solution?
My model doesn't have ice, it has only water. So I would treat snow as very, very, very cold water. Assuming that as soon as it touches very cold and completely zero salinity water. Assuming that as soon as it touches the water, it melts. If we want to account for freezing, and actually this overturning circulation, when does it happen? It happens in the winter. What happens in the winter is that there are intense winter storms that make the surface water of the ocean in the Arctic, make it freeze. Now, the salt doesn't freeze. So when the water freezes, all of the salt is expelled into the water, which makes the water underneath the ice that has just been formed. It makes it very, very cold and very, very salty, which means very, very heavy. This is what causes this overturning. So I guess if I wanted to treat ice in my model, I would have to kind of change the boundary conditions.
Okay.
So, yeah.
Have you done it in detail?
Sorry?
You mean you should change the boundary condition, right?
Yeah, I think so, because
Have you
instead
done
of having this, you would have this.
Have you also done this in detail? With the new conditions? Like for example, if you consider Antarctica.
No, I actually solved it numerically only in a box itself. But I mean, the numerics are pretty easy to modify.
Okay.
And the proof doesn't change from this. I mean, this is just any change in the boundary conditions in sources. So for example, you could treat an underwater volcano, for example, which happens in the oceanic ridges. There are underwater volcanoes. This could be treated as a source of high temperature and high, well, not salinity. Tracer is spelled there. It's all contained under this model and under this proof. It doesn't change the. So this is still true even if there's ice or snow.
Okay, thanks.
Yeah.
Are there any more questions? Okay, so let's thank Ori again.